Hey everybody, my name is Josh and today I'm joined with Amog and we are AP Tutor. So today we're going to start the first of a series of videos on AP Physics 1, how to tackle it, and some common problems. But today we're going to start with the first unit, 1D kinematics. So obviously let's start with the question, what is kinematics? So there are two basic so we start with kinematics. Kinematics is the study of motion and how to predict motion. So this will answer questions like, how fast are you going? How much distance are you covering? And how long it'll take you to do something. Like how long will it take a ball that I release to touch the ground? So this will answer questions like, if I kick a soccer ball like that, how far away will it land? That's something kinematics answers. Dynamics, on the other hand, is what causes motion. Like if I drop this ball straight down, what's pulling it down? So spoiler alert, this is the force of gravity. That's what dynamics will answer. And don't worry if you don't understand much of this, because this unit is about kinematics, and this is what we'll be learning today. So before we kind of dive into the math of this, we have to know two things, what vectors and scalars are. So a scalar is just a number. It's a number with units. So these brackets just mean what units. So this unit is a meter, for example. So a scalar can be any number, 3, 9, 420, and 2. These are all scalars. Sometimes you'll see them with units, so I could put 2 meters. So these are some examples of scalar quantities. So distance in meters. So a distance could be 10 meters. A speed could be 15, and units of speed would be meters per second. And we'll see why this is later on. Mass is in kilograms normally. You can also use grams. Volume, since distance is in meters, volume is distance cubed. That would be meters cubed. So let's say 5 meters cubed. So a vector is basically just a scalar, so like a number with units, plus a direction. So displacement is a distance plus a direction. So we have our 10 meters, let's say to the right. Our velocity would be 15 meters per second down. And acceleration, we haven't really talked about this yet, but we'll get into it on the following slides. But the acceleration will have units of meters per second. So we could say our acceleration is 21 meters per second down. And that would be a perfectly viable way for describing it. So now let's start with distance and displacement. So we remember from the last slide that distance was just a scalar. It's a number with units of meters. And displacement is the vector form. So for displacement, you'd add an arrow or something. So this is the thing about displacement. Say I was walking on a trail and the blue path is my trail. I start at the start of the trail, the head of the trail is point A, and my final spot, the end of the trail, is point B. So let's try to come up with a single number that represents my entire trail. So I start here. I'm going kind of at like a 45-degree angle up. Oh no, but here I'm going down and then I'm going up. It's like, there's not really one number that can describe the complete passage. So for that, physicists came up with displacement, which is basically how far do you go? Your final spot and your initial spot, that's all that matters. So distance is just a number, it's a scalar. So let's say this blue path right here is 200 meters. No direction, because I'm kind of going in every direction here. I'm going up and I'm going down here. However, displacement, you can make a direction. So say this line between A and B was 10 meters. And this is more or less to the right. So we could say, right, this is a vector. It has a number, units, and a direction. This is just a scalar. Why is it a scalar? Because it doesn't make sense to put a direction on this, because you're going in a bunch of different directions. So as you can see here, displacement is just a line between your initial and your final points. So let's try to mathematically describe this. So displacement is symbolized by delta x, and this is the Greek letter delta. Delta just means change in. So my change in is going to be my final minus my initial. So final is f. Initial is what's called naught. Naught just means initial or 0. So in this case, that would be b minus a, which would be 10 meters. And since b is to the right of a, I would tack on my right. So what's interesting about distance versus displacement, say I started here, I ran around the entire world, and I came back to the same exact spot. Well, what would my distance be? It would be the circumference of the Earth, the equator. I'd go straight through. But my displacement would be 0, because my initial and my final spots are the same. That's what's interesting about this. And now let's talk about time. So if I run around the whole world in 5 seconds versus someone else who covers the whole world in 2.5 seconds, who's faster? Obviously the other person. But how do we characterize this? So let's talk about speed and velocity. So speed and velocities. We know speed is a scalar in units of meters per second. We'll talk about why that is. And velocity would just be adding our vector. So let's try to figure out how do you find out who's faster? So it's who covers the same distance in a faster time. So it's distance per time. So let's say at my track meet, I covered 100 yards in 10 seconds. I know Usain Bolt, that wasn't my real time, sadly. And my friend Amog, he's on the YouTube channel, he covers the same distance in 20 seconds. And honestly, for those of you in track, that's pretty bad.
We also have your gym mile stats. You can't lie like that.
Hey man, I'm a sprinter. You don't gotta bring that up. All right, but back to this though. So we know it's distance per unit time. Distance is in meters per kind of division per second. So this is gonna be the same for me and Amog. But since I covered it in less time, I'm gonna have a higher speed. So we can kind of characterize this. You can see by the units how this would work. So speed and velocity are both described using the letter v. If you want velocity, you just put a vector sign over it. And that would be your displacement, delta x, remember, it's displacement, divided by your time. So if I covered a higher distance in the same time as Amog, I would have a faster speed. Or if we covered the same distance in a smaller amount of time, I'd have a bigger speed. You can kind of see how when this denominator gets smaller, that's going to go up. So if you remember from the last slide, this is our final spot minus our initial spot over time. And that's the idea here. But let's talk about what happens if my speed is changing. Like if I take off the first 10 yards of my 100-yard dash really, really fast, but then I start getting tired and my speed starts slowing down as I go. And again, those of you in track will really understand what I'm saying. And that brings up the concept of acceleration. This is interesting because it doesn't really have a scalar counterpart. It's just always a vector 100% of the time. So the units here are meters per second. And this is always a vector. So you need this direction no matter what. If you don't have a direction, it's wrong. However, some people might ask you for the magnitude of acceleration or magnitude of any vector, for example. If they ask you for a magnitude of a vector, that's just the scalar version of it. So just skip the direction, just give them the number plus the units if they ask for magnitude. So let's talk about acceleration. So let's say I start the race at 0 meters per second. And of course I'll do that. I don't cheat, no false starts here. And within the first 1 second, I jump to 5 meters per second. And then I'm pulling some Usain Bolt trick right here. I go to 10 meters per second, another second. So each second, I'm going up like this. I'm getting faster and faster and faster. So if you look at this, what's going on? How do we quantify this? So I'm definitely getting faster. So each of these bars are representing 1 second. So in each second, here I'm going up 5 meters per second. Here I'm going up 5 meters per second. Basically, each one I'm going up 5 meters per second. So acceleration with the vector is how many meters per second I'm going up each second. So this is the meters per second right here. These are the seconds. That's where you get the unit of meters per second. And since these both are in the denominator, they're normally just put together in meters per second squared. So as you see here, I increased my speed by the same number 5 each time, each second. And that's going to be the case with every question in this unit. So this is called motion with constant acceleration. There are cases in physics where this won't be the case. You'll have changing acceleration, like this will go from 0 to 7 to 10. Obviously not constant acceleration, but that's not something you have to worry about right now, so don't sweat it. So now let's move on to free fall. This is not a vector or a scalar or anything. This is just a state of being. So imagine this was Earth, this big piece of a circle Earth. And I take the ball and I drop it. So free fall is the state when you're purely influenced by gravity. There's nothing else, just gravity. So for example, you couldn't have air resistance. Air resistance is when you drop a paper, how it goes left and right and left and right. It doesn't fall straight down. It kind of like takes its time through the air because the air is kind of pushing it up. So air pushes up on everything. And free fall is the state when there's no air resistance. There's just gravity pulling down. So this would be called the force of gravity. You don't have to worry about any of this right now, but just know that free fall only works when you have just gravity acting on something. So the special case here is that some questions might ask you, okay, this ball is in free fall, or air resistance doesn't matter. Air resistance is negligible is the word the AP College Board normally uses. So if I drop this ball from 5 meters in the air, how long will it take to hit the ground? And that's something you have to answer using free fall. So for that, you have to know the acceleration of an object in free fall, no matter how big it is. So if I drop a ball and I drop like my computer, probably wouldn't do that. Drop a ball on my computer. The computer is obviously heavier than the ball. But if I drop them, if there's no air, they'd end up at the ground at approximately the same time. At the same time, actually, if there's no air. You can try this at home. If you take one heavy object and one light object, well, not really a feather because you need air resistance to be very, very small. But if you drop them, no matter how heavy it is, they'll end up at the ground at the same time. And this acceleration is called g. It's a constant number. It doesn't change. Basically, while you're on Earth, like near the surface where, this is me right here, near the surface where I'm standing, g is equal to 9.8 meters per second. Sometimes they try to trick you and they bring the whole experiment to the moon and they tell you that g, the acceleration due to gravity, would be like 1.6 meters per second squared. In that case, use this for acceleration and everything. So now we'll move on to talking about the kinematics equations. All right, so now we're going to start diving into the math behind these problems in kinematics. So how exactly would I go about solving this? So for these, you need the big four. They're called the big four glorious kinematics equations. So why are they so good? Because, so let's look at the variables in here. There are 5. Displacement, initial final velocity, time, and their acceleration going through that time. So the great thing about these 4 equations, and you can try this out for yourself. If I give you any 3 of these, so if I give you like this one, and this one, you could find me this one. Like, for example, with these 3, right here, right here, right here, I could solve for that. And it's possible for any combination of these variables. And that's what's great about it. So now you can look at these, write them down, put them in a picture frame to make them look nice. But now we'll take you through how these actually work. Because I don't want you to take my word for it. I want you to actually try to figure out how these work. But these equations are actually so important that they are everywhere. They're even in our title image. If you look at this, they're right here with different letters, but they're all here. So if you were eagle-eyed enough to catch that, then congratulations, you now have bragging rights. Well, let's move on to why these work. So your VF is equal to V naught plus AT here. Final velocity is equal to your initial velocity plus your acceleration times time. Well, this is kind of easy to prove. You know that acceleration is your change in velocity divided by your time. How much meters per second you're changing each second. Remember, we talked about this. So this is equal to your final minus your initial. Remember, delta is change. Multiply t on both sides. So if I were to add this to there, I would get the same exact thing. You know what? Let's write it down. I'm just adding this to both sides. So for the next one, we might have to learn a little bit about graphs. So this right here is a velocity versus time graph. So for any given time t, between 0 and 5 at least, I could tell you the velocity of my object. It could be a paper plane, could be a ball, whatever. So for that, let's learn about graphs. And a key thing here is to understand that your displacement is going to be your area under a VT graph. So if you have a graph of velocity on the y-axis with time on the x-axis, displacement is always going to be this area under here. Again, don't take my word for it. Try to figure out why. So let's try to figure out. So if this is a rectangle, constant velocity, 6 meters per second all the time. So our area under this is a rectangle. It's going to be base times height. Remember from geometry. So this is going to be your velocity is the height times your t, which is the base. All right, that's great. So we know that velocity is equal to displacement delta x divided by t, multiply t on both sides. This is also equal to vt, which means that these two are the same. Then area also has to be equal to displacement. So all right, that's all well and good. If I have constant velocity, then this works. But what about if I have non-constant velocity? What if I have some weird parabola-looking thing like that over here? Well, this kind of gets into some advanced mathematics, but if I put some rectangles under here, like these rectangles down here, I can try to get a good fit for what the area under the curve is. So you can notice that this is like a bit over, and this is under. This kind of overestimates. This underestimates. And this is still a little off. But if you notice that, you can think about it too. As these rectangles get smaller and smaller and smaller, and the heights are still good up here, you'll better and better and better get to approximate the area under that curve. And that basically says that the area under this curve is equal to the area of the rectangles under the curve. And we know that is equal to displacement. So if you want to learn more about why this works, this is actually covered under calculus in much better detail. So if you want to learn more about this, take calc. But let's go on to figure out why this one works again. Coming back here. This VF plus V naught over 2, this is just like your formula for an average, A plus B over 2. So we call this V bar. Bar just means average. So you might see this in other places as V bar T. So let's take a look at this graph. Again, it's velocity versus time. So let's sketch out the area. So let's draw this and this. So this is the area we're looking for. Let's label this as V naught. This is our initial velocity. You see that right here. This is velocity. This is your final velocity. And from 0 seconds to 5 seconds, that's the amount of time that you take. So now let's figure out our displacement. We know displacement is equal to the area. Kind of turn your head to the left 90 degrees. You see it looks a bit like a trapezoid. It is a trapezoid. The area of a trapezoid is A plus B over 2 times H. So this is your H right here. This is A, this is B. So you know your A and B are going to be V naught and VF. So your initial and final velocities times your height, which is T. And that is the same thing we got up here. It is proved. Now let's move on to this. Probably one of the more funny looking equations out of the bunch, but it's still possible to prove. Actually doing it a very similar way. Actually something I have to touch on though, I kind of forgot it. Going back here, you notice how this is a line? Well, since acceleration is equal to your change in velocity divided by time, we know this from before. Acceleration is the slope of a VT graph. And since this is a nice straight flat line here, the slope of a line is constant, so acceleration is constant. If this was some weird scribble curve, this derivation wouldn't work, and this equation would be wrong. In fact, that's kind of a theme with these kinematics equations. Only works. It's like a warning. Only works when A is constant. Don't use it. Just don't use it when A is not. In fact, if your acceleration is not constant, then try to break it up into stages where it is. But for the most part in this unit, that won't be a problem. So now let's try to figure out how to prove this. Well, I got this nice graphic here. So as usual, our difference between our times is going to be T. This is going to be V naught and V final. So our area is just going to be, our area, total area at least, is equal to displacement. That's equal to area 1 plus area 2. That doesn't really look good. So area 1 plus area 2. So this is area 1, that's area 2. So let's look at area 1. What is area 1? It's just a rectangle. The height of that rectangle is V naught and the base is T. So it's base times height, which is V naught T. So that kind of looks here. You see where we got that from? Second area is a triangle. So it's equal to 1/2. So this height is VF minus V naught. So let's call it delta V times T. It's the same, base times height. Base times height. So some of you might be looking at me funny. It's like, hey, this does not look like that. So let's make it look like that actually. So we know that acceleration is equal to change in velocity over time. Multiply time on both sides. Your delta V is equal to AT. So then this right here is equal to 1/2 AT times T. Remember, there's another T there. That's equal to 1/2 AT squared. And you look at that. If you add A1 plus A2, you know that our displacement is equal to total area, which is equal to A1 V naught T plus 1/2 AT squared. And that's it. We proved it. Now, this is probably most I considered probably one of the most fun equations in all of kinematics. But the reason it's so good, it's called time independent. And that's because there's no time in it. And if this equation is true, like don't take my word for it, we're going to show you why it's true. If this equation is true, then it's possible to calculate things without even using time. So like if I just threw a ball, you could figure out how far it went without knowing how much time it took in the air. Like I find that weird, but it's actually true. So there's just no time in this at all. So how do we figure this out? Well, let's start by kicking time out of the equation. So let's start by our kinematics equation. We know this is the previous one. Let's solve for time. Try to kick time out of it. So subtract this from both sides and divide by acceleration. And let's take another one. So we know that distance is equal to, displacement is equal to, add the velocities, the average of the velocities times time. Now you might have recognized this from algebra as kind of like a systems of equations proof. But if we know t is equal to that, and we can just plug it into there. So let me just rewrite this a little bit to make it simpler. So we can just switch these because they're added. You'll see why I did that in a second. So we know that t is equal to vf minus v naught. And this is just 2a. You can see how I got there, right? Now simply multiply this on both sides. You can see where we got the 2a delta x from. Plus v naught times vf minus v. So there's kind of a big hint right in this picture how you can finish the problem. And if you feel inspired, please pause the video and try to take over for me and come back and see if you're right. So hopefully you've had a go at it, and let's figure out how to finish this problem. So if you remember from algebra, we have an identity a plus b times a minus b is equal to a squared minus b squared. So if we call this our a and that our b, it's a plus b times a minus b. 2a delta x is now equal to vf squared minus v naught squared. And last but not least, we add this to both sides. And that's it. Our last and final equation has been proved. As usual, remember, these equations only work for constant acceleration. Only work for constant acceleration. All right, so that's enough of me. You've probably got tired of my voice. So I'll hand it over to my friend Amog, take you through some practice problems, hopefully get you familiar with it.
All right, everybody, I'm Amog, and I'm going to be taking you guys through some practice for 1D kinematics. So hopefully you guys paid attention to the lesson before, because now we're going to be using some of the techniques we learned from equations and 1D kinematics concepts to do some practice problems. So this is the first practice problem, and I recommend that you guys pause the video right now, try this practice problem out on your own, and then come back once you're done and see how you did. So hopefully you've paused the video, and now we're going to get started. So we have a car that's traveling along the highway at a speed of 15 meters per second, and over a period of 5 seconds, the car uniformly accelerates to a speed of 45 meters per second. In part A, we want to find the car's average acceleration over that time period. So to find the car's average acceleration, let's first write down the quantities that we know. So we know the initial velocity, 15 meters per second, as it says in the problem. We know the final velocity, 45 meters per second. And we know the time that it took to travel this distance, which is 5 seconds. What we want to find is the acceleration. So if we think back to our kinematics equations, one equation which really well relates all these quantities is Vf equals V naught plus At. And then at this point, since we have our equation out, we can just plug in our quantities. And our answer is 6 meters per second squared for the car's average acceleration. In part B, we want to find the distance traveled by the car over this time period. So once again, let's write down the quantities that we know. We know the final velocity, we know the initial velocity, we know the time. And from our last part, we calculated the acceleration. So since we know 4 quantities, we can technically use one of 2 equations. We can use delta x equals v naught t plus 1/2 at squared. Or we can use the time independent equation, vf squared equals v naught squared plus 2a delta x. Now, at this point, although this equation does work, this equation requires less quantities and therefore it makes it easier to calculate. So we're going to plug our values into this equation to get our answer. And so we get that the car traveled 150 meters. So now we're on part C. The light in front of the car turns red and it uniformly slows down to rest over a distance of 30 meters. And we want to find the new acceleration of the car. So it's important to remember that now we're talking about a new time period. So we can't use our initial velocity of 15 meters per second like in our last period of time. Now the start of our period of time has an initial velocity of 45 meters per second. So we need to factor that in. As so writing down the quantities that we know, we have our initial velocity, as I said, 45 meters per second. We have the car, we know that it uniformly slows down to rest. So we know the final velocity, which is 0 meters per second. We know the distance over which it slows down, and we want to find the acceleration. So similar to part B, we can use that same equation, the time independent, which relates these quantities together. then we can just plug in our quantities. And we get our acceleration of negative 33.75 meters per second squared. And finally, in part D, we want to find how long it takes the car to come to a stop. So once again, similar to part B, we know 4 of our quantities: the final velocity, the initial velocity, the distance, as well as the acceleration, which we calculated, and we want to find the time. So we know that it has a constant deceleration, so that way it's going to have a constant average velocity. So technically, we could, in this scenario, use delta x equals v bar t, or as you saw Josh write it, delta x equals 1/2 plus v naught t. And then we can plug in our quantities. And then solving, we get that time is equal to 1.3 seconds with significant digits. And that's the first problem. Okay, so now we're going to do our second practice problem, and this is going to be a graph problem. So as with the first question, I recommend that you guys pause it now, try and work it out on your own, and then come back and see how you did. And so hopefully you guys tried it on your own, and now we're going to go over the solution. So in part, we have a velocity versus time graph of a truck below, and in part A, we want to find the average acceleration of the truck over the interval t equals 0 seconds to t equals 140 seconds. So since it's a velocity time graph, we know that the slope of a velocity time graph is the acceleration. However, it's also important not to forget our kinematics equation. And since we remember that acceleration equals the change in velocity over the change in time, we can see that the initial velocity is 0, the final velocity is 0, and so the change in velocity, delta v, is also 0. And since delta v is 0, the average acceleration is also going to be 0. Sort of a trick question. In part B, we want to find the acceleration of the truck over the interval t equals 0 seconds to t equals 20 seconds. So here, it's not another trick question. We have an actual final value for our velocity and an initial value. From 0 to 20 seconds, we know that it goes from 0 meters per second to 20 meters per second. So just like we could use the slope formula, we can similarly use the same formula in the last equation. Acceleration equals the final velocity minus the initial velocity over the change in time. And so if we can just plug in our values, the acceleration equals 20 meters per second minus 0 meters per second over the change in time, which is 20 seconds. And so we get that our acceleration is 1 meters per second squared. Moving on to part C, we want to calculate another acceleration, this time over the interval t equals 120 seconds to t equals 140 seconds. So we have our initial velocity and we have our final velocity. So we can once again use the same equation. Acceleration equals the final velocity minus the initial velocity over the change in time. Plug in our values. Our initial is 50 meters per second. Our final is 0 meters per second, I meant. Sorry about that. Minus our initial of 50 meters per second. And remember, we're just talking about this time period from t equals 120 seconds to t equals 140 seconds. We divide by another 20-second interval, 140 minus 120, and we get that the acceleration is equal to negative 2.5 meters per second squared. And it's important to note the negative because the truck is slowing down, and also you can see that the slope of the graph is negative, and the slope of the velocity graph is the acceleration. So the acceleration is negative. Now, in part D, we want to find the displacement of the truck over the interval t equals 120 seconds to t equals 140 seconds. So just like we have a velocity time graph, the slope of the velocity time graph is the acceleration, but the area underneath the curve will be the distance traveled. So this area right here will be the displacement of the truck. Now, we don't need to use any fancy calculus to do this because we can see here, since there's a constant slope, that this is just a triangle. So we can just use delta x equals v bar t. And we know that that's also can be written as delta x equals 1/2 v naught plus vf times the time. And so we know our initial velocity, our final velocity, and the time period. So we can do delta x equals 1/2 50 meters per second plus 0 meters per second times the time of 20 seconds. And we get that the truck travels 500 meters. And you'll also notice, looking at this equation, that it kind of looks like the area of a triangle equals 1/2 the base times the height, which is the change in velocity, and the base is the time traveled. Finally, in part E, using our velocity time graph, we want to sketch an acceleration time graph for our truck. So as I've said multiple times throughout this problem solving experience, we know that the slope of the velocity time graph is acceleration. So all we need to do is find the different slopes and write them on our graph. So we can see here that the average acceleration, if you remember from part B, over this interval is 1 meters per second squared. So we can just draw a line at 1 from the time t equals 0 seconds to t equals 20 seconds. Then from time t equals 20 seconds to t equals 50 seconds, we can see that there's no change in velocity. So the acceleration must be 0 over that time interval. Now, what you can do is you can draw a directly vertical dotted line or straight line connecting these 2 points, but it's not necessary since the acceleration change is instantaneous. Now, we can also see from time t equals 50 seconds to t equals 80 seconds, the velocity changes from 20 meters per second to 50 meters per second. So we can just write out our formula for acceleration. A equals delta v over t. And since we know that the change in velocity is 30 meters per second, 50 minus 20, over a time of 30 seconds, 80 minus 50, the acceleration there is also just going to be 1 meters per second squared, just over a longer time interval than it is from t equals 0 to t equals 20 seconds. So we can just go ahead and graph that. Once again, from t equals 80 to t equals 120, we can see there's no change in the velocity. So once again, our acceleration is just going to be 0. And finally, from t equals 120 seconds to t equals 140 seconds, we have already calculated this in part C. We found that the acceleration is negative 2.5 meters per second squared. So we'll just go underneath our graph. And 2.5 should be somewhere around here. And that will conclude our acceleration time graph. It will also conclude our second problem. And that's all for today's video on 1D kinematics. So we hope you guys learned something. Hope this has been useful to you in your AP Physics 1 journey. And if you guys are liking what you're seeing, be sure to leave a like, subscribe to our channel, stay tuned for more videos on AP Physics 1 and other AP subjects. If you guys have any subjects that you want us specifically to cover, be sure to leave something down in the comments. And thanks for watching.